Hi, I'm Jingfeng. I'm happy to talk about our work in EMNLP 2020, planning and generating natural and diverse Disfluent text as augmentation for disfluency detection. This work was done in Seattle lab at Georgia Tech. Disfluency detection is a very important task in NLP. For example, if we have a sentence from transcribed speech, like I want a flight to Boston to Denver, disfluency detection is to identify disfluent segments in such sentence and transform it to a fluent sentence, like I want to fly to Denver. So disfluency detection is the first step of preprocessing transcribed speech for machines, and then a machine can use such fluent text in other downstream NLP tasks. Disfluency generation is the inverse task of disfluency detection. Disfluency generation is to transform a fluent text to corresponding disfluent text. So disfluency generation can help text-to-speech system to generate more natural speech. Besides, it can also help disfluency detection. The way of using disfluency generation to help disfluency detection is to use augmented disfluent data in disfluency detection. It can help solve the problem of lacking annotated disfluent data to train disfluency detection models. We follow such schema. In the first step, we generate fake disfluent text with disfluent segment labels as augmented data. Next, we use augmented disfluent data to pre-train the disfluency detection 6 labeling model. Finally, we fine-tune the disfluency detection model on gold label disfluent data set. One of our major contributions is to generate natural and diverse augmented disfluent text. It can solve the problem of prior works. Previously, people used disfluent text generated by random insertion or repetition of n-grams as augmented data, but such disfluent data are not natural and they do not resemble gold disfluent data. We propose a new disfluency generation model. In the first step, we use a planner to choose which positions to insert different segments. Next, we use a generator to learn and generate natural disfluent segments in picked positions. Here is an overview of our planner generator PJ model. Basically, a planner predicts where to insert disfluent segments, and then generator will generate disfluent segments from such position. Here we show our disfluency generation results. We report the blue score and sentence accuracy, which are two automatic metrics to measure naturalness of generated disfluent data. We can see that our PG model outperforms all other baseline models in terms of these two metrics. Especially PG model outperforms the insertion and repetition methods by a large scale. Then we use a variant of our PG model, the PGNC ADID model. In this diagram, we can see that the PGNC ADID model also outperforms the insertion repetition methods in all of these 5 metrics. First, it outperforms the insertion repetition model in terms of blue score, sentence accuracy, and human evaluated naturalness, which means that our model can generate more natural disfluent sentences because it also outperforms the baseline model in terms of diverse 1 and diverse 2. It can also generate more diverse disfluent sentences. Finally, we report our disfluency detection results. Our baseline model is a BERT6 labeling model. After adding augmented disfluent sentences generated by repetition and insertion, it improves the performance. After we add the augmented disfluent data generated by our generation model, our BERT repetition insertion generation model further outperforms the BERT repetition and insertion model in terms of F-score. That's because our model performs better in terms of recall, which means the disfluent sentences generated by our model can help disfluency detection model to identify more disfluent segments without harming the precision. If you are interested in our project, feel free to check out our project page. Thanks.